Where was it? He is here. We just calculated in our example 1 for the case where the impedance was infinite. Okay, we came up with the voltage on the line is 2V0 plus cos of beta z. So I'm just using that, saying that's the same case. So that's where I came up with this guy. Okay, and then, so this, I have some line voltage as a function of position, and that position goes from z equal to 0 to z equal to minus L. So if I look at this voltage, what the line tells me it should be at this point z equal to minus L, all I have to do is, so V at z equal to minus L, the line impedance, I'm going to call that line to separate it from. So that's what the transmission line tells me the voltage should be. That's equal to 2V0 plus cos of beta L. Or I plugged in minus L in there. And by the way, the cosine is an even function, so for cosine, minus b sub L is equal to cosine of b sub L. It's the same thing. So that's why I ended up to V0 plus cos of b sub L. Okay, so that's what the transmission line tells me the voltage should be at that value. And my source is V sub S, so that should be the same as the source value voltage. Yeah.
What's the subscript of the V?
Sorry, which one?
Of the V, so the V something,
Here?
parentheses Z equals negative L, to the left of that.
This one?
Yeah.
Line.
Oh, line, okay.
Yeah. Thanks for asking, by the way, because everybody agrees my handwriting sucks. We all concur. Thanks. So this should equal to V sub S hat at Z equal to minus L. Because here, Kirchhoff's voltage law, this voltage has to be the same as the voltage that is going through here. So if I just look at the absolute value, so the absolute value of V sub 0 plus is V sub S hat over 2 cos beta L.
How did you get to that?
Sorry?
How did you get to that part, V plus the absolute value, Vs?
Oh, so I got it, let me. So from here, okay, I just get V0 plus is V sub S hat over 2 cos beta L, right? So that's the general function. And all I'm doing with the absolute value is saying then the amplitude of V sub 0. So don't think about the phase of the signal, just worry about the amplitude. Ends up being the amplitude of this guy. Ooh. This is a sign. I'm being dramatic, guys. To the dropping the hammer on you guys. So what does this mean? If I have an unterminated transmission line and I have no source resistance, okay, the voltage that I launch into the transmission line is going to depend on the length of the line, because look at this. I got the length of the line, cos of length of the line here, right? So depending on how, just physically, if I make the line like a meter long or a meter and a half or whatever, I'm launching a different voltage in there. Why is that? Because that voltage is a combination of what my signal generator is doing and what got reflected back. Okay? So and then remember also that when I have an open, remember when I said you have an open circuit, open load or high impedance load, you get standing waves? Means like Doesn't matter, like, it'll like get reflected back, reflected back, reflected back. So at any point in time, if I look at that load end, it's getting stuff reflected back if it's a continuous input. Okay? So the situation, this is the first place for really like weird results, which seems, this is like, there is some reality to this, but also it's kind of an extreme. Look at the special case. This is, I warned you guys ahead of time that it could give some seemingly nonsensical results. There's a special case of beta L is equal to pi over 2. Okay, in that case, cos of beta L goes to 0, and I get an infinite voltage launching into the transmission line. So infinite is usually like not realistic in the voltage domain, it's not realistic. Okay, so something is up. So what happens in real life? So let me talk a little bit about that. So essentially what happens in this case, you go to V0, the amplitude of V0 plus, which is the V0 plus again is what gets launched into this transmission line. That amplitude is V sub S hat over 0 in this particular case, which goes to infinity. Okay, so it's not true that it goes to infinity, but it is true that it gets very large. That part is true. Okay, in fact, this is something called so as an aside, this is called a quarter wave transformer. QWT. And it's when the length of the line is the wavelength divided by 4. So because somebody asked me earlier what the definition of beta was, the definition is 2 pi over lambda. So 2 pi over lambda times lambda over 4 is equal to pi over 2 in this case. And you end up with, for a given wavelength, a given size, a given length line with an unterminated end gives you a very, very large input voltage because of this interference. So we're going to come back to this. For the L,
is that the length is equal to lambda over 4?
Yeah, quarter wave. What's your name?
Alexandria.
Alexandria, thanks. So one question you might have is, what's this wavelength? Okay, so we'll see in a little bit, but the wavelength is related to the frequency of the signal and kind of the speed of the light in this material. Okay, so I'll come back to it a bit, but the faster a signal is, the shorter the wavelength. Okay, so what does that mean? Like, by the way, I'm just sometimes I meander because I think about stuff to tell you guys. That might be amusing. So your cell phone, right? Do you guys know what frequencies these guys transmit at? Like our 4G or whatever? It's roughly a couple of gigahertz is the actual, like the carrier. 5G is like, I forgot what it is. I think it's like 5 gigahertz or 5 something. 5G, by the way, doesn't stand for 5 gigahertz. Somebody said that at some point, and I was in a bar or something, so I thought it was better not to correct them. But